Okay. Nice to see you, hardcore lot. I'm honoured. Okay, this is one of the last two lectures we're going to do on the additive. And this one has some elements which you do need to know. We've talked a little bit about it throughout the whole module. But next lecture will be on Monday, and that won't be necessarily part of any examination. So that's obviously me shooting myself in the foot, seeing none of you turn up on Monday at 4 o'clock. Maybe I'll be the only one by that stage. On Monday we'll talk a little bit about the computer-aided engineering modelling of additive, which is something that we should do a lot of at college. I'm very interested in, and I hope that if nothing else out of interest, you'd come along and have a look at it. But this is something which is very much at the forefront of additive manufacturing. So we're going to talk about material properties of parts as they come out of the machine. It's a bit of a stumbling block for some of the processes. So everybody wants to compare the properties, as it's a relatively unproven technology, of additive-based parts, particularly of powder bed. So they want to be able to have all the flexibility of a 3D geometry that you can make at the push of a button, but they want to have all the properties that you might expect from, you know, a single crystal nickel superalloy that goes into a turbine blade. And that's often not quite fair on this process, and it's something which I'm going to show you some properties as we go through. I'm going to show ways of measuring those properties and reasons you would use particular testing techniques to test those properties. So I'm going to start probably quite basic, and I always tend to forget with you lot that there are a mixture of people who have a materials background and people who have a mechanical background. So I've tried to kind of find an intermediate. Some things are going to be very easy for materials people and not so easy for the mechanical, and vice versa. So bear with me. So normally I would have done this in this order. The mechanical properties coming in last, a little bit on the computational modelling, which we'll do on Monday. We've already done design rules. We've done a lot of that on this module because you've had such a practical which was involved in actually sort of designing from scratch to be able to make a part. I know they weren't turbine blades. Often they were more like bottle openers, but that's fine. The process of going through that design 4 a.m., we've covered a lot of that. So you probably know more than you think you know on that side. But yeah, as I said, the properties. So until over the last year and a half, there's been and undoubtedly it's going to continue. There's been a lot of progress on the metal side, particularly in terms of the improvement of the machine in terms of the reduction of porosity. So whereas it was quite normal to see high levels of porosity in the parts with previous machines, maybe no better than 3%, and sometimes as bad as 10% or more. That, in this most current generation of machines, we're looking at less than 1%, even 0.5% porosity. So the porosity has improved, but it's still there. Residual stress is still a big problem. There's shrinkage of the parts, which you may have noticed in some of your parts, to actually achieve the tolerances that you might have expected was not quite as easy as you think. You had all those support structures on there, which I'm sure you realize are not quite as easy to get off as you might hope. Those support structures that pin it to the base plate and the high temperatures you get are the things that lead to residual stresses in parts. So these are the number of defects, high surface and roughness. We're going to talk about that a bit, and step geometries. But one of the problems is that even low levels of porosity in parts cause reductions in the mechanical properties. You expect that. And I like this old graph here, which is more about powder metallurgy, and there's a lot of similarities. So in powder metallurgy, you get relatively higher levels of porosity. And this shows how the different mechanical properties that you might be interested in from tensile properties to fatigue properties all the way down to the elongation impact, how they're affected by relatively small amounts of porosity. And you can see in that first instance of less than 5% porosity or inclusion, and we have both at times, there are very drastic drops in some of the properties, particularly elongation and fatigue strength, even with relatively small amounts of porosity. And because, to a certain extent, for critical applications such as aerospace, you will always be compared to the best possible properties of the material. Even that small amount of porosity is going to give you a disadvantage. So even if you're at 1%, you're still looking at a reduction of up to 25% in the elongation and impact energy, and potentially a reduction in fatigue strength, which is greater than you would hope for. A lot can be done to reduce porosity, but there's always a trade-off. So you do heat treatments, you get a trade-off. So our properties that we are very much interested in are roughness, density, hardness of materials, elasticity, tensile strength, fatigue properties, creep properties, and then of course when we're processing it we need to know about the thermophysical and chemistry properties. And all of these arise from various defects which I've already mentioned before. So what we're going to have a look at here is how we measure surface roughness, how we measure the density, what kind of values we would get from additive parts, and potentially how I'll talk about how these compare to what you might expect. We're going to go through these in that order: roughness, density, hardness, elasticity, tensile properties, some fatigue properties. I'm not going to touch on the final ones. We could be here. This is really a large subject, so we are condensing this into less than an hour. So we won't touch on creep or the other properties. These are, and I think that it's important to understand that the functionality. So if you are in a materials development program, you will often get set, right, okay, a target for a specific alloy, and that target will be set based upon what they're expecting of it in service. So I'll be referring a lot to turbine blades because they have often the harshest working environments and the highest safety requirements. So you might get typically a table like the one on the right there, where the company, Rolls-Royce or GE or whoever is developing the material, will tell you, right, we're going to replace the material you're using for that specific turbine blade with the material you're going to develop in your program, but we definitely need it to match this. So they might give you a specific requirement of the proof stress to be at a specific temperature to have 300 MPa, or stress rupture of 300 MPa at the same temperature over a duration of 30 hours. They'll give you a creep target, they'll give you a fatigue target, and they'll then determine whether it's high cycle or low cycle fatigue, and how many cycles they expect out of that material. And they'll have very set pieces, tensile pieces. So these are very hard targets that the material has to meet before it even enters a higher technology readiness level scale within the company. So they will then, that is your first target. If you can achieve those, that's great. But then that's just the beginning, because then you have to go through, that might just be TRL3, then it has to go through a development of the process plus the material. Is it possible to do on a larger scale? Then it has to be FA certified, then it has to go through engine testing, or land engine testing, and then finally it'll go through a flight testing. And it'll be a long time. This is a 10-year, 20-year program of development of materials. So that's why we don't have alloys coming out every week. These take a long time to develop. And it's not just in aerospace. that you'll have that kind of, they'll change depending on the location within the engine or the part itself within an airframe structure. But you have them set for right down to small components in automotive, and satellites have their own requirements, satellite components. There's a few, I managed to sort of separate out of some publications. It's often very difficult to get hold of this data, so unless you're actually working in that industry, you might not know it, and you're not going to go behind one single paper and list it all. So you have to kind of have worked on a few of these projects to see this kind of data. We can start right back from a very generic perspective, and this is something that you guys have got access to with the CES selector. You can see across a whole scope. So there's always trade-offs between materials, and there are some trends between materials. You can look at the differences in hardness right across from polymers through to metals, and you can see the general trend of hardness with elasticity there. So you can have your metals on the high end here of the elastic modulus, and that has a sort of, the hardness, the higher the elastic stiffness, the higher the hardness, as you would expect. But within that, you can have materials which defy the odds in a certain way. So I was just reading a very interesting paper by a group from Lawrence Livermore who work in additive manufacturing. And we've had a few contacts there with a guy called Wayne King, who runs the group. And they published this paper in Nature saying how it was possible with a material like 316 that they worked with to overcome the traditional trade-off between tensile strength and elongation. So often you can get very high tensile strength at the expense of elongation in the material. And they were saying that additive gives you the possibility to engineer the microstructure of the material because the laser is so small. Often we see very low elongation for the parts, and you get a lot of anisotropy and things like that, which I'm going to show you about in some of the results that I've got on here. But they were saying that if you choose the laser properties correctly, you can get super high elongation with very, very high yield and upper tensile strength by literally combining builds in the additive machine, by optimizing the lasers and using a lot of computer modeling and tensile tests to match them all together. And literally right from down almost up to the nanoscale, they're actually engineering the microstructure. And it's a hierarchical thing which actually allows it to have the super elongation. So there's some very interesting properties that you can get. But there's always these trade-offs. And selecting a material, so this is a, I'm sure you've seen these before. Again, there's a typical Ashby diagram showing density versus Young's modulus there. So you can see our high-end alloys for aerospace up on this higher density range and having the high stiffness by Young's modulus. Fracture toughness and yield strength as well. So these are just examples of some of the material properties which we're talking about here. Young's modulus versus strength. Again, you've got polymers and then your metals on the high strength, high Young's modulus N. I love those diagrams, they're great. You can spend hours just looking at all the different materials. This is something that came out relatively recently, and it's related to AM. So using an Ashby style diagram, they're trying to look at some of the more common alloys which are used in the powder bed systems, particularly. This is by a chap called Ian Todd from Sheffield. And so he came up with an index. So that's what these Ashby diagrams come up with. They come up with an index which allows you to kind of determine your trade-off so you can select your materials. And they thought that it would be interesting to look at coming up with an index of processability of the additive of the alloys to see if they could group them into what they knew were alloys which were easy to process and more difficult ones. And they come up with an index which was related to shock resistance to avoid cracking during the builds, but then also one which had a good dimensional stability there in terms of thermal expansion and various other properties that they kind of lumped in together. It was interesting, but I can't work out how it works. And it was interesting because it does show, where they've drawn that line, some of the more common alloys, which are very processable, and which all the machine makers tend to work with. So you've got 316, and you've got 174pH, and the Inconels are well known for being very well easily usable. And Ti64 is not far off that line there. So in that kind of area, those are alloys which are easy to process. And then they've got some further up, so tool steels, miraging steels, steels which require some sort of heat treatment afterwards to sort of retain the kind of tensile elongation and hardness properties. And they're more difficult. So everything above the line is actually more difficult. And then they've got Invar right on the top right, and they've got aluminium on the top. So they seem to have got some sort of coherence in the diagram, which I agree with. But it's upside down. So I don't understand. I'm still trying to work out how this works exactly. And I just wanted to show you, because I thought it was an interesting sort of progression through from using Ashby diagrams across all alloys to specifically what they're doing with additive. I think maybe it's a little bit too generic, but it is interesting because it does show that some of the alloys which are difficult to process are on that top side of the line. But you wouldn't expect to see them there, because as far as I can tell from this, higher shock resistances from left to right and higher dimensional stability is from bottom to top, so you would expect this to be the other way around. But hey, maybe they got their index the wrong way around. I don't know. Right, let's get into some of the properties for additive. How do we measure surface roughness? Well, we'll use a probe or white light lithography. What is it exactly? Well, it's trying to measure peaks and troughs as you go through. All processes result with, there is always some form of surface roughness. You never come out with something which is completely polished. We will have, we measure the surface roughness as a dimension. So the most common one is the RA, but you have another one, RZ. RA is the lowest of these, and this is measured in micrometers. And it will be a, it's an indication of the average between the peaks and the troughs, as you find out. But where you put that average is not that clear. You can use a profilometer, which is the most relevant one. It's very easy to use. You just literally run it along, and you can do stretches up to about 10 millimeters. And that will give you an indication of surface roughness. So how does that compare across different processes? Well, I've got a graph, a table there sort of showing all the way from metal cutting to casting, forming. And you can see that for all of these processes, with some subsequent treatments, you end up with ranges from very rough, where we'll be up in the sort of 50 micron range, down to very smooth, where we'll be in sort of nanometer ranges of roughness. And across all the processes, if we were to look at what comes out from our powder bed or powder bed fusion or electron beam or selective laser melting or whatever you want to call that additive process, we are consistently in the rough end of the spectrum. So particularly the E-beam, electron beam, which comes, and this is related to the spot size, the particle sizes. E-beam uses really large particles, has a relatively large spot size of the beam, so about 150 microns. Particles are about 100, 150 microns, so they're large particles. Our powder bed processes use slightly smaller particles, 15 to 45 microns, but with a 70 micron spot size. So obviously, if you take them straight out of the machine, you've got semi-sintered powder on the side. That will give you surface roughnesses above 25, 30 micron. If you sandblast it, you can get rid of those particles, and then you're down to a kind of natural state of the material, and then you probably won't be much below 12 micron, 12 to 15 micron. So that's still quite rough. Even from casting, from sand casting, you would expect that kind of roughness when it's you've been in contact with the sand. So we are dealing with a process which is coming up with relatively high surface roughness. You've seen that on some of the parts that you've made. You know, and that's titanium, which is relatively smooth compared to some of the other materials we work with. So yes, it's a rough process, and that is something which a lot of work's going on with the machine makers to try to reduce that. You can play with the powder size particles, your spot size, the layer thicknesses, all of these to be able to try to reduce it. Polishing is always going to be a problem. If you make a very complex 3D part, you're going to have surface roughnesses which vary across the part. There may be parts you're never going to be able to get into polish. And that natural underlying roughness is partly to do, not entirely, but it is partly to do with the digital nature of additive manufacturing. So the fact that you've got discrete layers, we've also got discrete spots. So our system particularly works in a series of spot welds. So between those, you've got potentially a kind of undulating form. Across the hatch spacing, you've got another set of undulations. So there's your natural frequency of undulations that happen on the surface. As you go up the layers, you build the layers up discretely in 30 micron or 50 micron. If you're trying to fit a curve, then you're going to have some sort of like anti-aliasing as they have in bitmap. So this stepping gives you an underlying surface roughness, beyond which all you can possibly do is hope that by polishing it you can get rid of it. But again, then you're back to that original problem of how do you polish complex underlying surfaces. The angle of inclination, so if you were to do...
So,
yeah.
I have a question from 2 slides ago. There's grinding and there's milling. So I'm just wondering if you had 3 types of post-processes, grinding, milling and sandblasting, which one would you expect to give the roughest surface finish then?
Probably the milling.
The milling.
I would think, yeah.
And the finest would be grinding?
Yeah, sandblasting would be sec. Grinding, yeah, the grinding would, it all depends on how you interpret that. I mean, you know, grinding we see is from a materials perspective. If you're trying to polish up a sample, very nice flat face, you know, you go through a sort of series of grinding and then polishing steps. So yeah, your grinding would be your first one, and then your polishing, you'll start to bring in sort of finer and finer sandpapers, and then finally you have a diamond mix or something which will polish up the surface. I'm not quite sure if you're referring to this kind of abrasion process. Yeah, that would put it in that order as well. Grinding would be the sort of higher surface roughness. Yeah, I think really on this part I was really more interested. I think I don't quite think of abrasion as it's a sort of reduction step rather than a processing step. So the metal cutting and casting and forming, etc., is component manufacturing processes. So. Yeah. When we look at this anti-aliasing, you can see there are relationships which follow the sort of almost like a geometric progression in the surface roughness, which can be matched through studies. This RT is another form of measuring surface roughness. The RA is the one there, and depending on the inclination, you can have various measurements. Different types of. I think you've seen this graph before. You can see here there are 3 different types of powders with a 30 micron layer thickness. But these types of powders, what I haven't got on here is that the powders are actually. So if you have a coarser powder, you have a higher surface roughness. If you have a finer powder, which is that blue one there, you have a lower surface roughness. So that's surface roughness talked about a little bit. Density. Okay, when we talk about density, and really what I'm trying to get at is porosity. Okay, so there are various ways of measuring density. So we can use good old Archimedes, dip it into water, and we can compare that to the density of the water. And possibly begin some corrections for density of air, and it will come up with a value of density. we could actually try to measure the parts, but that's actually quite tricky unless you have a very simple part. So there's errors relatively large errors that can go as high as 20%, 30%, just in the way in which you measure. The smaller the parts, the lighter or the less dense the parts. So if you're trying to do an aluminium, those errors in the measurement become very important. As the porosity goes down, it gets even more difficult to measure the density. In terms of if you're trying to work out the difference experimentally between something that's got 0.5% porosity and 0.7% porosity, it's actually very, very difficult. So at that point is when you sort of tend to rely a little bit upon microscopy. And what you'll do is you'll section the part in various ways, and you'll take lots of small images, as small as you can, patch them together, threshold them in such a way that you can pick out porosity, which will typically be for very low porous parts that you have now. Will typically, you'll have maybe a little bit of what we call macro porosity, maybe a couple of 20, 30 micron size pores that are clearly there, but what you can't see from that is your micro porosity. Anything that is below 1 or 2 microns becomes very difficult to see and capture. But all of these can add up. So that combination of micro and macro porosity will potentially have as much as a 25% influence on some of the mechanical properties that you're going to be measuring. In the old days, in the old machine, this is the A250 that had 200. We were able to see, these are sort of comparison of measuring the relative density by microscopy using direct measurement and Archimedes as well. So you can see we forced this sample C12 to have such laser settings that the porosity was as high as 40%. And at that point, you have the opposite problem, that if you're going to use Archimedes, you've got to make sure you coat it so the water doesn't ingress and influence your results. But generally, you can see that as we increased the laser energy input here, we went from having a high-level porosity to a peak here where you're about 2%, 1 or 2% dense porosity. And then as you overcook the laser settings, you've got too much energy density, then you start to have, and possibly through keyholing and through other ingression of gases into the melt pool and things like that, the porosity starts to increase, and therefore your relative density goes back down again. So we would pick out from this some of the optimal parameter settings which gave us the highest density. And that was relatively easy in the old days because we didn't have that much laser power, and we were getting much larger overall densities. And nowadays, though, where we're looking at, instead of that sort of best bet 1%, we're actually almost, the best bet now is almost 99.999% or even 100% dense. And it's more difficult to pick out where the optimal is. Let's just show you some of the porosity, and you can see unmelted powder particles in there. You can see the individual directions in which the laser has moved on this, and the sort of interstitial non-coverage of the laser, which leads to these. These are quite large pores, quite angular and jagged as well, which are going to give you stress concentrations when you go on to do your tensile tests. As you get up to your sort of more optimal settings, here you are, one of the better ones, your porosity sizes go right down. So we're talking still macro porosity. What you can't see, obviously, on this is the micro porosity. And then we've gone past the best point, and the pores start to increase. You can see the more rounded shape of the pores. And this is by no means data that or results that we've had only. These guys from in the US, even using higher power lasers, see this combination with power and speed. You can still see this kind of almost, there's always a peak. So it's a power law which tapers off with your higher energy density. And there's always some way of picking out, even with the higher lasers, you can pick out some sort of optimal point where you are between having too much power density and too little power density. So it's still there, even with the better machines. I'm talking about porosity and density there. Hardness is one which I'll bring in because a lot of papers do talk about hardness, but I mean it's a difficult. It's not difficult. It's only an indicator. Hardness for us is only a very rapid indicator of what kind of mechanical properties you would expect from the material. Now, you may have seen some of these machines down in the metallography lab. They're for measuring hardness. Vickers and Rockwell are just different scales, and you basically the whole idea behind that is you drop a loaded, a very sharp pointed object spike into the material, and it measures the indent, how deep it goes, and also how it comes off at the sides, and the different kind of heads that they have to do the indentation will determine the type of testing, whether it's Vickers or Brunel or Rockwell or whatever. So here are some of the different scales. That's what, so you obviously you get the measurement from the machine that tells you about the indentation, but then you can also look at the images and look at some of the sort of fracture stress lines that happen around the indentation. To give you a bit more detail, so this is some measured hardness for hip and aluminium tensile bars, both. So they've done a few tests on this, and you can see that the as-built is typically quite hard. That's probably indicative that you're going to have a very high yield strength, high upper tensile strength, but potentially quite brittle. And then when you do a heat treatment such as hipping, it'll soften the material, bring the hardness down, maybe restore some of the elongation. You can see some discrepancy in hardness in different directions as well. So that's for some aluminium. Here's for 316. You can see a slightly higher Vickers hardness. You still get that softening with the heat treatment. So if you've got a horizontal and a vertical, you can see slightly harder built in the horizontal direction to the vertical direction, but both of them getting softened with the heat treatment. And for 17.4 pH, now 17.4 pH is a precipitation hardened steel, which is often used for tool steel. You can see the very high levels of hardness that you would expect from that there. Elasticity. So obviously this is like, it's going to be very easy for you to understand elasticity. You've seen it for years now. As far as the design perspective and the design of a component, elasticity is incredibly important. It is difficult to measure though. So you can get elasticity properties from tensile tests, but they're not always the most reliable way of getting it. So compliance of the tensile testing machine means that you may have as much as 50%, 60% error in your elasticity measurements. You can use other things like ultrasound and also sort of vibration tests, and they are sometimes more accurate. We're interested in terms of the elastic properties that we're interested in. We're interested in Young's modulus, the shear modulus, and the Poisson ratio. This is the area where I'm talking about now. So it's the point, the linear. The small linear in steel alloys is the small linear part where you can return after small strains without suffering any sort of plastic deformation. As I said, you can use ultrasound as well. So that's one of the techniques which we've been working with, where you take a ultrasound signal and you send off both a longitudinal ultrasound signal and a shear signal, and you time the, you take the time, or the machine gives you the reading on the time that it takes to do a set distance that you can measure, and with that you can use you can derive the velocity of sound in the material, and you can, certain equations will give you back the Poisson ratio and Young's modulus. And here are some of the results from that. So the black lines represent a 316 material, a steel, which would normally have about a 200, so the 316 in maybe a wrought form, or the quoted values are around about 200 GPa for the Young's modulus. And you can see here various laser settings that were put into the 316. So there is a lot of porosity in these. These are the same samples that you've seen the porosity for. So the samples with the large amount of porosity down here with the low input laser power, the power density here, and we're talking almost half the Young's modulus, partly probably because of the interference of the pores. And then as your laser energy goes up and you reduce the porosity, you get a peak point. The black lines represent the as-built material, and then what we took is take the same material and we hipped it, hot hydrostatic pressed it. So we're getting rid of the porosity in there, so theoretically it's 100% dense. But what you can see is that even though we'd got rid of the porosity through hot hydrostatic pressing it, we still had a reduction of the, or at least as measured by ultrasound, you can see there's a reduction there in what it should be over the theoretical 200 GPa. And there's a peak point here. So this was telling us that actually the way in which we built that material with the laser, it was actually modifying the microstructure in such a way that it was actually having an influence upon the elasticity properties of the material. And this goes back to that paper in Nature that has been out recently. I was telling you about that there are things that you can do with additive which on the surface may look, oh, that's not very good, but in actual fact, if you can tap into that modification of the microstructure down at such a small level, you can influence as much as the elasticity properties and everything. So it's actually quite exciting. And again, in peak here, Poisson's ratio derived the same way. You can see that there's a peak, a change with the power density input. Right, tensile properties. So we've kind of been building up to this a little bit. So there are lots of standards. There's ASTM standards, and all the samples that you can make will give you different stress strain curves, and it's quite a. It takes you a long time to develop the right samples. What we're looking to get here primarily is the yield strength, the upper tensile strength, and then the elongation to fracture is indication of the ductility of the material. So those three things are what we would normally quote a particular material by in terms of the tensile properties. Here are some different ranges that you would expect from different alloys. Lower UTS with aluminium, wide range with copper. The trade-off there is always between the upper tensile strength, the yield, and the elongation. So materials that have typically have good elongation don't necessarily have such good tensile strength. There's various titanium alloys. The one that you guys have worked with here is the Ti64, an alpha-beta titanium alloy, and you can see here quite high yield and UTS, relatively low elongation. We're going to see some stress strain curves from various additively made parts horizontally and vertically, and then so you'll see that. Here are some of the changes of those mechanical properties. So tensile strength will reduce as a function of temperature. In fact, most properties go down. although you might get a slightly more elongation, but yeah, here are some of the nice stress strain, true strain curves here of various different alloys. So you've got some of aluminium, steels, brass, 3046 steel. So let's say the reason that I'm giving you all of this is so that you may, if you're working with additive in the future, come up on a test program in the company you're working for, and they say, right, okay, we want to replace this part which is made by casting, or we're going to replace this part which we typically machine out with one of your great 3D additive parts. How are the tensile properties going to compare? How are you going to choose a tensile test component? How are you going to show that it has the same properties regardless of the direction it's built in? And you've got a lot of flexibility in additive to be able to make those tensile bars. You might not have so much flexibility in other processes, and you're going to have to cut out big sections. So you can net shape them. Are you going to have a cylindrical format? You're going to have a round tensile test bar, or are you going to have a net shape rectangular dog bone type test bar? And what sort of dimensions are you going to do to accurately capture the real properties of the material? So that's something that you need to think about very carefully. And we've been through, and we see a lot of parts coming through with Rolls-Royce now. With electron beam, they're very interested in electron beam, and there's still a lot of variation. They still haven't decided what is the right tensile test bar to use, whereas they might have some very standard tensile test bar shapes for specific materials. With additive, there is no specific. We are actually testing test bars which are no bigger than 55 millimeters at the moment, which is slightly outside the ASTM scope, which requires you to have a certain width to height radius ratio. And here are some of the problems that you get. So this is the Ti64 material which you made your parts from, and you can see that in the top left there, which is the almost as-built, so note that we haven't actually got as-built tests here. Bearing in mind that a wrought Ti64 should have a yield strength of about, so if we go back to the sort of these values here, we're looking at a UTS of somewhere between 990 MPa to 1,200, say. A yield strength somewhere between, say, 800 to 1,000, and an elongation somewhere between 2 and 30%. So let's assume that this 1 hour or 2 hour of annealing doesn't make a massive amount of difference, which it actually does. But you have quite a large scatter in the elongation. And there's a difference between the parts which are made vertically and the parts which are made horizontally. So almost inevitably, and almost across all the alloys and different materials that we've tested, the vertical direction is never as strong as the horizontal direction. Okay, so the bonding between the layers for AM always results in that. And it doesn't matter whether you're working with plastics or whatever. So it's literally that you're not getting that bonding between the layers on the way up. So when you pull it in the direction it was built, it is inevitably weaker than when you pull it across the layers. So that difference in strength. Here, you don't see that much difference in the elongation, so it looks quite scattered. All right? And that may be more particular to Ti64 than anything else. But what you do notice is the elongation is relatively on the low side, so you should be getting 2 to 30%, and hopefully more like 30% elongation. But we're getting something which is relatively brittle, but much stronger. Well, not much stronger, but relatively stronger. So our yield there is looking somewhere between 1,000 and 1,200. The yield on the quoted tables for a forged type Ti64 is probably about 200 MPa lower. So we've got high strength, low elongation. These heat treatments, the 2-hour annealing and then a more aggressive, higher temperature in the second one, change the elongation. So that's one of the things that heat treatment does. It makes it more ductile. It makes the material more ductile. But you still get, although you've improved the elongation, you've still got quite a bit of scatter after just a simple heat treatment, which is like without any other. Hot isostatic pressing has made a big difference to elongation. So you've actually, and it's also reduced the scatter between your parts. You can see it softened the material a bit, and it's actually become more like the forged in terms of the strength. And then, of course, that trade-off between the tensile strength and the elongation is clearly apparent there. It's by heat treating and by hot isostatic pressing, it's managed to bring down the yield strength and the tensile strength, but it's introducing much more ductility into the material, and you're getting 17%. But that is still a long way below the 30%, which is quoted for forged. And this is kind of, if you look at across different materials, so that's titanium, and this is a nickel alloy, 718, it's the same thing. The heat treatment does the same thing. So it's not rocket science. This is something which we've always dealt with materials. In this case, we've got a very clear difference between the vertical and the horizontal builds. So that one up there, which is the as built and machined. So these are quotes. These are the built ones. You can see that the vertical is not only not as strong in yield and UTS, but it's also got significantly lower elongation. And we see this with the Invar material, the 316. Aluminium is particularly the case, where you've got much lower elongation, so much more brittle type of alloys that we'd work with. But the heat treatments do pretty much the same thing. Interestingly enough, with this one, even when you do hot isostatic pressing, although you've managed to increase the elongation, you still get a very big difference between the vertical and the horizontal. Now, I don't know if this was something, these are Renishaw results, so I don't know if they got something funny going on with their samples there or not. I don't know. But it wasn't our testing. This is our testing. Just to repeat the same thing, there's a lot going on there. So 316 is very ductile compared to those other materials. You would expect a 30 and up to 60% elongation on this austenitic steel. But the relative change with heat treatments and with hitting, it does exactly the same thing as with the other alloys. By heat treating, you improve the ductility, and you soften the material, you bring down the tensile properties. So this is just more repeats of what I've already said. Just to kind of finish off with a final set of properties. So fatigue, you know about fatigue a little bit. Yeah, put it in the machine. So you'll have high cycle fatigue, low cycle fatigue. It just depends on how many times you can put in different waveforms, the amplitude of the waveforms, and you're looking at some sort of repeated development of small cracks, which is developing bigger cracks, the failure of the material. What you're really ultimately interested in is how many cycles a particular material will undergo before it fails. These are SN curves, so you'll be given at a particular amplitude of the stress. You'll take it through and see how many cycles it will do. Here are some comparative figures for the fatigue strength of different materials. So you can see stainless steel relatively low there at 200 MPa, and then going up to some quite hard and strong materials like cobalt chromes and titaniums. Samples are slightly different, and it's particularly important with fatigue specimens that you have a very smooth, polished surface, so that the surface doesn't actually influence the cracking of the part. We've got two fatigue machines which are available. Well, there's one fatigue machine available for students in the heavy structures lab if you're interested in looking at it. That's the Instron, and then there's a Phoenix benchtop fatigue tester which does high temperature fatigue at higher frequencies. So the frequencies are 200 hertz, I think. All right. I can't remember exactly what the frequency is. High frequency on the Phoenix benchtop on the right, and then it's low 1 to 10 hertz on the student machine. These are some results for TR64. So these again are results from Renishaw, and these are cycles to failure. So this shows you again that those two they had 3 different heat treatments on TR64. Here they're showing one. The first one was the stress relieved at 730 C for 1 hour, and then you have a more aggressive hipping treatment. So that improvement in tensile properties is mirrored in the improvement in the fatigue properties. But what is interesting is that on this graph we haven't actually got the fatigue results for a forged material. So they're only comparing it with an additive material. If you look at the sort of higher stress, you'll be looking probably the curve for a wrought material will be down here somewhere. So you still, even with hipping the material, your fatigue strength is quite a long way away what it would be with the wrought. And again, this is with 718 from the same batch of testing, that the as-built and then the heat-treated and then the hipped is improving the fatigue properties, but again, they haven't got on there the forged, which would be expected to be much higher again. Not well, much higher, probably up here in this region here. So that was all I was going to put over. There are obviously other properties that are important, but we are probably at quite an early stage with AM, so there's a lot of work going into, particularly if you think of that as a progression of mechanical properties. We were involved with a project called Amaze that came to a finish last summer, and they had a massive campaign of testing TI64 built in lots of different ways, electron beam through to wire, arc additive plus powder bed, you know, to a certain extent this massive campaign of testing the material was a little bit too early on in the stage of the development, because there was a wide range of different results coming out from the different processes. They're all at different stages of development, and if we had repeated the same tests that were done 2 years ago with the machines now, all the results can be very difficult. So that, although is a continuing effort on behalf of people who want to use additive, and it is very much a focus on the mechanical properties which come out from additive parts, is still something which is going to have to be ongoing, because of the improvements from generation to generation machine are happening within 1 or 2 year spaces. So that's the end of that. Any questions? We've got a couple of minutes. There's a lot to take in, but I hope that gives you an overview of where we are with some of the typical mechanical properties. I haven't been able to update that with all the testing we've done over the last year. So we have got some interesting results with Invar, aluminium, some new 316 results, but it's just getting them all summarised for you is a big time job. So. I haven't mentioned other trade-off properties which are equally important for different applications. So one of the things that we're going to be looking into over the next next year or so is about the corrosion properties of. So that's also something which could have hidden benefits. We don't know, but it also could have problems. So okay. If you have any questions, fire away. If not, I'll see you on Monday.